What is a counting unit? It's a numerical grouping, and we use them in everyday life. Some examples of them happen to be the dozen. We know how much is a dozen, right? 12. How much is in a pair? 2. And Ricky, you told us how much was a ream worth? 500, yes. And a gross back there. 144. And then the score was 20. These are all daily things we use. We might not use scores, but I use pairs and dozens quite a lot in my life. And I use reams a lot because I have to copy lots of sheets of paper. But when you go to the store, you buy things in different units, amounts, and this would be that. So we're going to be talking about the counting unit, though, for chemistry. And it happens to be called the mole. And so we're briefly going to watch a video here with the mole song. Pay attention to the words, though, because it will describe the counting unit of the mole, and it'll give you really good analogies of how to think about this unit. Okay, so in regards to the pennies from the mole song, what would happen if we all had a mole of pennies?
That's like enough to finalize.
Yes, everybody would be super, super rich with trillions of dollars, and it would, yes, kind of ruin the economy, but that's a whole nother issue. But everybody would have tons and tons of money because 6.02 times 10 to the 23rd is such a big, huge, huge number. And what about the paper? What did they say about the paper in the song? Going back and forth to the moon 80 billion times with these little thin sheets of paper. But if you had a mole of paper, that goes a very long distance. And what happens to us about the marshmallows if we had a mole of marshmallows on the earth? It would block out the sun, and we'd all have to be eating for how many years did it say? Like 40 million years, and that was when it was back in the 90s when they thought we had, like 5 or 6 billion people. We could probably get it done in more like 35 million years now because we have more people, but still, it's quite a task at hand because that's such a huge number. The mole is a huge, huge number. Now, in reference to atoms, though, what are we talking about there in terms of how big is the mole? Pretty dang big. A couple more little references here. Soft drink cans would cover the Earth depth up to 200 miles. Popcorn kernels would go all the way up to over 9 miles. And another way to think of it is able to count atoms at 10 million per second. It would take us about 2 billion years to count all of the atoms in one mole. Yes?
Where do we write for how big is a mole?
How big is a mole? A mole is 6.02 times 10 to the 23rd. Okay? And the mole was based off of, well, it is Avogadro's number, yes. The number of atoms in 12 grams of carbon-12 is where the calculation was done for Avogadro's number. Avogadro himself wasn't actually the one who calculated it, although he gave us lots of wonderful things, especially in terms of gas laws. So it was kind of giving him credit by naming the number after him. Like Einsteinium was named after, an element on the table. Same kind of idea there. Avogadro's number, 6.02 times 10 to the 23rd. Now you guys all know the right pickup line you can use. I wish your name was Avogadro, because then I'd already have your number. Because now you know this number. Ha ha ha, right? You got that? So you can use that from now on. Okay? And it is 6.02 times 10 to the 23rd of anything. It is a counting unit. So you could have a mole of cookies. Now, we don't really measure our cookies usually in moles, but you could have a mole of cookies and it would be 6.02 times 10 to the 23rd cookies, and we'd be back in the marshmallow problem of having to block out the sun, and we'd have to eat quite a lot to survive.
You know, cookies will last you a lifetime.
I think more than one lifetime. Probably, you know, four what, billion lifetimes or million lifetimes, whatever it was.
That's big.
Okay?
That's pretty big.
So, 1 dozen cars would be 12 cars, but 1 mole of cars would be 6.02 times 10 to the 23rd. And if you're looking here at aluminum, though, if you had a dozen aluminum atoms, that would be 12. But if you have 1 mole of aluminum atoms, you would have 6.02 times 10 to the 23rd. Now, I want to show you real quick. We set up a vial and a beaker over here of 2 substances, and both contain 1 mole of that substance. This vial contains water, and as you can see, the vial is a little bit skinnier. And this beaker contains salt, sodium chloride, in it. So what do you see about these?
One of them is clear and one of them is white.
I'm talking in terms of amounts. Looks like there's more salt than there is water, good. But in both of these, there is 6.02 times 10 to the 23rd, and here this would be molecules because it's covalent, because water is covalent and shares. And for sodium chloride, we call these formula units because it's an ionic compound. So you do notice that the sodium chloride mole does seem to have more in it than the water mole. And I'm going to tell you why in just a minute. Okay? But both of these are 1 mole of the substance. 6.02 times 10 to the 23rd particles are in each one. How do you measure a mole? Let's talk about that. Great, great question. Everybody filled this in? Moving on to the next part.
Will be about like 10 seconds.
Okay, so in chemistry, the mole will usually be one of the following representative particles. So atoms is one choice. These guys, atoms, if it's labeled with atoms, it's going to be elements directly off the periodic table. So if they're saying atoms, it's directly off the periodic table. If they're saying molecules, molecules goes with covalent compounds. So anything that are non-metal are going to be considered molecules, sharing electrons. Ions are going to be any atoms off the periodic table that have charges, like Na+1, Cl-, Al3+. Okay? Could be CO3-2. What's CO3-2? Remember that ion? What's that ion? Carbonate. Okay? So any of those fall in the ions category. And last but not least, our lovely formula units over here. Formula units are always ionic compounds. Ionic compounds are, of course, going to be metal, non-metal, or polyatomic with a metal or ammonium in there. So remember, atoms are the elements off the periodic table. So you would look to the periodic table for the elements. We call those atoms. Molecules are covalent compounds, non-metal, non-metal. Ions are going to be atoms that have a charge, or a polyatomic would be considered an ion. And then ionic compounds are for formula units. These are how we label the particles when we're using Avogadro's number, 6.02 times 10 to the 23rd. All right, moving on here. So, 1 mole of carbon, what would we use in order to address that one? What would be the label that goes with 1 mole of carbon? It would be 6.02 times 10 to the 23rd, yes, for 1 mole of carbon, but which one of the labels would we give it? Atoms, molecules, ions, or formula units? It would be atoms, good. And for 1 mole of H2O, which label would you give that? molecules because, yes, water is non-metal, and therefore it's going to be a covalent compound. So it gets assigned molecules. What about sodium chloride? I heard a formula units out there, and you are correct because it is an ionic compound. It is a metal and a non-metal. So you would label it there. Now, if you decided to dissolve like the sodium chloride in water and break it apart into its ions, Na plus would be considered ions, and Cl minus by itself, when it's formed there with the charge, it would be called an ion. If you broke it up into the ions, that's what it would look like. Okay. Any questions before we move on? All right, so molar mass. This is why we're going to figure out the sodium chloride looked like it had greater amount in the mole than the water has in the mole, because it's based off of its molar mass. That's a good key term. And the molar mass is the mass of 1 mole, and we use it in grams, and it has the units grams per mole, per 1 mole. So what you need to do to find a molar mass is you take the atomic masses off the periodic table for all of the elements in the compound, and you will add them up. Now, if you have one that has a subscript, you need to multiply that subscript by the atoms as well to get the entire masses of all of them. Multiplying the number of that, so you have each element by the mass on the periodic table. So let's take a look and do an example real quick together. Now you can write this down on the side there, or space where you have some room. If I'm doing the molar mass of sodium chloride, I have 1 sodium, right? Because there's no subscript there. So I go over here and I look at the periodic table. What does it tell me sodium's mass is? And we're going to do masses all to the hundredths, which is 2 decimal places to the right. So it tells me sodium is 22.99. So round to the hundredths. So this would be 22.99. Now, for the chlorine, what does it say its mass is on the periodic table? Looking over here, it says what? 35.45. And there's only 1 chlorine as well. So now what you're going to do, you're going to take those and add them up. And what do you get as a total mass here? 58.44. Good. And that would be grams per mole. Now let's look here at iron 2 hydroxide. Let's go ahead and add those up. Here I have iron. And what's iron's mass? Iron is pretty heavy. It's 55.85 on its own. Now we do have this little subscript out here to deal with. What does that mean about our oxygens and our hydrogens? How many total oxygens do we have in this compound? Actually, we have 2 because this would distribute, right? So there are 2 oxygens. So for oxygen, we need to multiply its mass by 2. And oxygen happens to be 16. So that's 32. Okay. It's 15.99 whatever, so we round it to 16.00. So for the hydrogen, how many hydrogens are in this compound? Also 2, because the 2 also distributes over here to the hydrogen. And hydrogen's mass happens to be 1.01, so that gives us 2.02. Now we can add it up because we've now multiplied by the subscripts. So we have 55.85, 32, and 2.02. We need to add all that up. So what do we get for its molar mass? Adding all that up, we get, yes. I'm sorry, what? Let's add it all up. .87, good. And this would be grams per mole. So, if we had 1 mole of sodium chloride and 1 mole of iron 2 hydroxide, which one would we need the bigger beaker for? Iron 2 hydroxide, because it's got about 30 something more grams in it. So we would need a bigger beaker to hold 1 mole of the iron 2 hydroxide than we would the sodium chloride. Okay? So everybody good with finding the molar mass? You need your periodic table out. You got to look up the masses. You got to add them all together of the number of each atom in the compound. We're going to use this later on as well. So moving on to one more conversion factor. There are 3. Avogadro's hypothesis states that equal volumes of gases, and yes, that's spelled wrong, I understand. Let's just cross that off. Okay, gases. Move this out of the way, can't see over there. Okay, that equal volumes of gases at the same temperature and pressure contain equal numbers of particles. And so we use this value because we'll calculate this later when we do the ideal gas law in gas laws. But there is a conversion factor that you can use for gases if you're at standard temperature pressure. And we call that STP, standard temperature pressure. Standard temperature is always 0 degrees Celsius. And what is 0 degrees Celsius a reference to? The freezing point of water. So we use the temperature of the freezing point of water as standard temperature. It is kind of cold, you're right. Standard pressure, though, is 1 atmosphere. Does anybody know what that's a reference to, 1 atmosphere? Atmospheric pressure, 1 atmosphere. This has something to do with the pressure of the atmosphere. But where is this going to take place? Where would 1 ATM or 1 atmosphere be? Would it be up at the top of Mount Everest? No, because the air would be a lot thinner up there, right? So we base this off of the atmospheric pressure at sea level. So it's 1 ATM at sea level. And you don't realize this because we don't really feel it, and our bodies and our skin are already adjusted to it. But right now, we've got molecules of air just bouncing off and putting pressure on our skin and our body. Right now, 1 ATM, well, we're in Northern Virginia, we're very close to the sea here, so we're probably more like 0.98 or something in terms of our ATM, but we're very close to 1 ATM. Okay? So that's what we use as our values for standard temperature pressure. 0 degrees Celsius, 1 atmosphere, you need to get that memorized. Now, at standard temperature pressure, we have a value for gases that equal 1 mole, and it doesn't change for any gas. It could be carbon dioxide, it could be hydrogen, it could be oxygen, it could be sulfur dioxide, it could be any gas, methane, ammonia. They're always going to be one magic number of volume, and it is 22.4 liters. 22.4 liters. One more time, 22.4 liters. So that number you have to get memorized as well. So 1 mole of gas always equals 22.4 liters at standard temperature pressure. And then we also have to get our particle number of Avogadro's number, that's 6.02 times 10 to the 23rd. That number has to get memorized. Okay? So we call the 22.4 number the molar volume. because it's any gas at standard temperature pressure, 1 mole equals 22.4 liters. So it is called molar volume. Now, I'm going to give this to you next class, but I will show this one up there. I did draw it on the board too. This is called the mole map. You'll get a copy of it to use. And over here they give you the balance that shows that you're finding the mass of something. And you'll use the molar mass to equal 1 mole. This all equals 1 mole in the center there. 1 mole. 1 mole. And then if you go up here, you would get your volume, showing the balloon that we're representing gases up there. And that number is the 22.4 number that you use. Yeah, so back for the mass, it was the molar mass that you would use as the conversion factor. And then over here, it's showing you like lattice structure and a bunch of the atoms. You see the representative particles. So that could be atoms, formula units, or molecules, or ions. It could be any of those things over here, and you would use Avogadro's number as the conversion factor. But all three things will equal 1 mole of any substance, okay? And that's what we're going to do now, is we're going to do some conversions. We're going to go back to those T-chart train tracks that we used at the beginning of the year. We're going to be revisiting significant figures at this time. So you do want to have your periodic table out, your calculator, and get ready to get back into T-chart mode. Okay, so let's take a look at some practice problems. So for here, I'm going to be converting the following mass values to mole values. You must know the substance in order to calculate these for the conversions, because you have to be able to look them up on the periodic table. So, first things first, I'm going to draw my T-chart, just like I used to before, and you don't have to do the beginning part of the T-chart, because you can do it right here. Now, does anybody remember from the beginning of the year when we have like grams here, and we need to get rid of grams because we're working it to moles? What do we do with that grams in the T-chart? We call it the diagonal down, diagonal it down, put it down here. Down it goes. And what we want should go on the top. And we want moles, so moles should go on the top. Now, we know everything's going to equal 1 mole, so I can put the 1 in there. But now I need the grams. I need the molar mass. So I need to get out my periodic table and look up the values. So you can do this on the left-hand side here. So for magnesium, what's magnesium's molar mass? 24.31, right? 24.31. We have 2 fluorines in this compound. So I need 2 times what? So it's 18.999, but we're going to round that one to 19.00. Okay, so that's going to give us 38, right? So now I take my 24.31 and my 38.00 and I add them together. What do I get for my entire mass then? So that gives us 62.31. So then I would put that in here, 62.31 for my conversion factor. And just to help you remember how the T-charts work, you multiply the top, you divide by the bottom. So what this really looks like and what it means would be 162.3 times 1 divided by 62.31. That's how you would punch it in your calculator. Okay? And let's get a calculator answer so we can round it to the correct number of significant figures. So yes, a calculator answer of 2.60471 blah blah blah. Okay. Now, like all of the other conversions at the beginning of the year, you need to go with how many you start with. How many significant figures are in this beginning number over here? 4. Remember, if it has a decimal point, you start from the left, go to the first non-zero, and count everything afterwards. That would have 4 digits in it. So over here in my answer, I only get to keep 4. 1, 2, 3, 4. Start from the left and start counting over. Now, with my 4, do I round it up to a 5 or leave it alone? The 7 next to it makes me want to round this up. Correct. So we are going to end up with 2.605 grams. No, I'm sorry. We got rid of grams, right? We're going to moles. No, it's moles. Right? We cancel out our grams. Grams get canceled. So we have moles, and then don't forget to write your compound down here. Magnesium fluoride. And then you would circle this as your final answer. Okay? So that's how you would do the top 4. You're going from grams to moles. So grams diagonals down, moles goes on the top. Let's try one down below, though, where we're going the opposite direction. We have moles, and we're going to change them into grams. So we have moles going to grams. So in this case, what happens now with our unit? What diagonal down? The moles will diagonal down. And we abbreviate mole, M-O-L. I know that's not much of an abbreviation, but you need to write M-O-L for mole every time. Don't just put an M because that will get confused with meter. So it has to be M-O-L. So then grams will go up top, okay? Everything equals 1 mole on our mole map, the mole map. So now we just add it up. K gives us what number? How much is K? Potassium equals 39.10 if we round to our hundredths like we're supposed to. Br is a little heavier. How much is Br worth? $79.9. It's heavier, yes. So add those two up, and how much do we get for our molar mass? So that ends up being 119.00. And I keep the .00s to remind myself I need to go to the hundredths every time. So this is going to be 119.00 is my grams. Now once again, remembering how the T-charts work, this is multiply, this is divide. So how this one looks would be 1.36 times 119.00 divided by 1, basically. So you can kind of mentally skip that step once you get in the routine again of dividing by 1 in your calculator. Now, significant digits for this one. How many do we get to keep in our answer? How many do we start with over here? 3. So how many do we get to keep over here? The calculator answer ends up being 161.84. So I'm going to keep 3. 1, 2, 3. Do I round up my 1 or leave it alone? There's an 8 next to it, so we round it up. This is going to be 162 grams now, because moles cancels with moles. And that would be KBR, because we want to put our substance here next to it. Okay? So you guys now work some problems on your own. Give you like 5 minutes. Okay, particle conversions. Let's look at particle conversions. Now, for this purposes, for the first set of practice, we're going to consider everything molecules. So everything's going to be considered covalent compounds. Okay, so we're using molecules as our designation. So we're going to pretend like everything up here would be from a covalent compound. So in order to do this conversion, you need which magic number? Molecules, atoms, formula units, ions, they all revolve around which number? What's the particle number? How much is in a mole for a particle? 6.02 times 10 to the 23rd. Avogadro's number is your conversion factor number. You don't have to look on the periodic table. You don't have to add anything. This is the conversion number. And that always equals 1 mole of any particle, sets of particles here. So if we have moles and we're going to molecules, who diagonals down? Starting with moles, going to molecules. So what goes on the bottom? Moles. And you can, I guess, abbreviate molecules, something like that, if you don't want to write out the entire word. So 1 mole equals how many molecules? 6.02 times 10 to the 23rd. Okay, so now what you're going to do is multiply and divide by 1 here. And you get your calculator answer is 1.204 times 10 to the 24th. Now, how many digits do we get to keep?
2.
We only get to keep 2. So I'm going to keep the 1, going to keep the 2. Do I round up to the 2 or leave it alone? Leave it alone. So this is 1.2 times 10 to the 24th molecules. And since they didn't tell me the substance, I can just write molecules there. Okay? So that is going from moles to particles. Moles to particles. Down below, going to work another problem, but this time we're going to start off with the particles, and we're going to work it to moles. Okay? So, let's do number 7 for fun. Number 7 says we have 1.5 times 10 to the 20 atoms of something. So it must be an element off the periodic table if we're talking about atoms here. So in this case, what do I diagonal down? Atoms. Atoms goes down here. So that means the mole, 1 mole must go up top. What's the magic number for atoms, formula units, particles of any kind?
6.02.
Avogadro's number. Yes, 6.02 times 10 to the 23rd. Now this time you're multiplying by 1 and dividing by the 6.02 times 10 to the 23rd number. So therefore, when you get your answer, how many digits do we get to keep in our answer? This one's coming out in scientific notation for me, so I'm just going to keep a couple digits here. How many do I get to keep? Only 2 again. Look, there's only 2 digits over here to begin with. So, I'm going to keep the 2. Do I round up the 4? Round that up, good. 2.5 times 10 to the minus 4. In this case, it's going to be moles of something. It didn't tell me what the substance was. Now, I'm going to show you once again how to punch these into the calculator real quick. I'm going to show you using both types of calculators.
Whoa.
I know, there's my shirt. Huh, okay, here we go.
Looks like the neon.
Here's my hand. Here's my calculator, and we're kind of twisted. There we go. And a little bit forward. Move it a little bit up. No, okay. There. Almost perfect, right? Okay. Now, like that number we just punched in, exactly this number, I would do 1.5. To use the exponent key, if you're using a graphing calculator, you need to hit the second button up here, and then the comma button right here above 7. That's the double E, which means exponent. So you type that in. Then all you have to do is put in the power on the 10. In that case, it was 20. And you do divided by, and then you do your 6.02. Once again, second, and then the comma button right here gives you the double E, and you do 23. And you hit enter, and you get your calculator answer. Okay, that's how you use the exponent key on the graphings. Now, if you're not using the graphing, you're using this guy. Okay, your exponent key is just slightly different. We would type in our 1.5, like so. But then we'd have to hit this EXP button down here. That's the exponent key by the equal sign. And we would do, and these two little zeros pop up. Then we type in our 20, which is the power on the 10. So the 1.5 double zeros pop up, and you put the 20 in there. Then you hit divided by, and you do 6.02. Once again, you need to hit that exponent key. The two little zeros pop up, and you need to type in the 23, like so. Hit equals, guess what? Now, this negative 04, what that means is 2.49 times 10 to the minus 4. That's what that means, times 10 to the minus 4. Does everybody see how to use the calculators again for the exponents? Because they get complicated, and if you try to use like the carets and the other buttons on them, you don't necessarily can get order of operations out of order and get the wrong answer. Okay? So there we have that. Alrighty, now we're going to go to page 2 and look at our gases. Okay, so looking here for the gases. What is the magic number for any gas at standard temperature pressure? How many liters equals 1 mole? 22.4, good. 22.4 liters of any gas equals 1 mole. Of course, this is at standard temperature pressure. That's 0 degrees Celsius and 1 atmosphere. Now, same setup. You don't have to go to your periodic table. You don't have to do any extra calculations. You just use the 22.4 number. So, I'm going to choose to do number 2 here. Okay, set it up. I'm going from moles to liters now. So who do I diagonal down? In this case, the moles are going to diagonal down. 1 mole equals 22.4 liters. Okay, so you just would multiply 0.75 times 22.4 divided by 1. And you get 16.8 liters. Moles cancels with moles. Now, how many sig figs do we need to have in our answer? We need to have 3. Good, there's 3 to start with. Guess what? Our calculator answer came out with 3, so we don't have to do anything to it. We just get to put a box around it. Oh, it's N2. Don't forget our N2 there. This is nitrogen gas. They do give us the substance, so we should insert that as part of our answer. N2, nitrogen gas. Now for the bottom one, doing the same thing, except for now you're going to go from liters to moles, And we call these all one-step conversions because they only take one train track to do it, or one T-chart. So here, if I have 5.0 liters of hydrogen, now what goes on the bottom? Which unit? Moles or liters? Liters will go down on the bottom. Good. Diagonal down those liters. So moles will go up here. 1 mole equals 22.4. It's the magic number. Now basically you multiply the top by 1 and divide by 22.4. In this case, we would get 5 divided by 5 times 1 divided by 22.4. So we get a calculator answer of 0.223214, blah, blah, blah. Now, how many digits do I get to keep? I have 2 to start with, so I get to keep 2 in the end. I keep the first 2. The second 2, do I round that up or leave it alone? Leave that one alone, 0.22, and this is moles, because the liters will cancel, of H2, and we do that. Okay, you can put this front 0 here, and that will be the end of those problems.